First of all, thank you for inviting me to participate in this conference. I thought the student presentations were absolutely impressive. I think the students deserve a round of applause. Okay, so I'll talk about the engineering science underpinning the extraction of beta-lanes, beta-carotenes, and these are basically valuable products which are extracted from, which can potentially be extracted from food processing waste. Beta-lanes can be extracted from beetroot processing waste, beta-carotene from, of course, carrot processing waste. So I'll talk more about the technology rather than the general market and other things, because I'm an engineer by profession and I can only talk about technology. Okay, both beta-lanes and beta-carotenes are from vegetable processing waste. Beta-carotene is also a precursor for the synthesis of vitamin A. Somebody had asked about B12 and other things. Like B12, vitamin A is also not soluble in water, so we have to absorb it from oil and such other media. So I'll talk about extraction of beta-carotene in edible oils. And then if these bioactive materials are recovered from vegetable waste, we clearly have to employ a process which technologists call solvent extraction. Beta-lanes, what kind of solvent you use will depend on what you're trying to extract. If you're looking at beta-lanes, then it requires a polar solvent like water. Water is a polar solvent, and then you can also change the polarity in alcohol and so many other things. When it comes to beta-carotene, it clearly requires a non-polar solvent, and edible oil is a very good medium for extracting beta-carotene. And I will show later in this talk how we can produce. See, nowadays most edible oils are sold. As edible oils. Why can't we fortify edible oils? The trouble with oil is everybody thinks oil is bad for health. I have to be honest, I love oil-containing products. I love fried foods. So and I think most of us do like fried foods. We may not. So why can't we fortify oils and make it a bit more healthy? That's the question that I'm posing. So, if you look at the extraction conditions for these bioactives, for a given solvent, the particle size distribution, the ratio, the substrate to the solvent that you use, all these are important. And if that is fixed, then clearly the extraction time and temperature become core variables. But there is a major problem, and the major problem is that these materials, these bioactives, are thermally sensitive. So from a process point of view, you want to use a higher temperature because then the extraction rates will be higher and production capacity will be higher. However, if you use a higher temperature, they tend to degrade. So these are the conflicting issues that we experience, and what I'm going to do is to talk about how we use engineering to solve this problem. So as a consequence of thermal sensitivity, what earlier researchers have done is to sort of lower the temperature. So they have observed relatively low rates of extraction, and therefore they have got relatively low yields. Most researchers have missed a turning point. See, this is where you have to be very careful. This is particularly an advice for researchers. Don't look at some previous papers and say they have used this 50 minutes, 60 minutes or whatever. Please think for yourself, is the temperature the right temperature? Is the time of sampling also the right or not? Because you can easily miss some phenomena which are occurring. So to remedy this, now since they have got very poor yields, what earlier researchers have done is to use very energy intensive and very poorly scalable technologies to improve extraction rates. I don't know how many papers there are in the use of ultrasounds for extraction. In my view, it's a totally useless technology. It cannot be scaled up. And what they are doing is more, if you look at the laboratory experiments they do, they take 50 ml of the solvent. It's a very small volume of the solvent and stick a 500 watt ultrasound probe in it. Now, if that's the sort of energy per unit volume, you will probably get in solar explosions, and you're not going to get that in a factory, in a food factory, definitely not. The other thing that they have also started doing is to use very expensive solvents. Both are undesirable, and we are doing this simply because we have really not understood the mechanism of extraction. So as an engineer, I'm trying to say, let's understand the mechanism of extraction and then see how we can achieve the productivity that we want to achieve. This is just a graph, data from some of the earlier researchers. Will see that in one case the extraction has been carried out at 30 degrees. 30 degrees is a very, very low temperature. You really can't get viable and economically profitable yields. And then of course you start using ultrasound and other things. So our hypothesis and approach is based on understanding of the engineering science of extraction. So first of all, we recognize that the extraction from the solid phase, which will be the waste, is accompanied by solute decomposition in both solid as well as the liquid phase. This is important. When a component is thermally sensitive, it is thermally sensitive in the extraction medium. It is also thermally sensitive in the waste phase. So that's the first thing to recognize. Appreciate that the extraction and solute decomposition are both rate processes which can be mathematically modeled. It is here that mathematics plays a very important role. So we hypothesize that the net solute concentration in the extract phase is given by a balance between the rate at which the solute transfers from the solid phase, between the rate at which the solute transfers from the solid phase and the rate at which the solute decomposes due to heat. So based on this hypothesis, we develop a mathematical model. And this is an isothermal model. That means the model is valid. So if you look at the solid phase mass balance, I apologize for those who are not very familiar with mathematics, but please note mathematics is important for engineering design and to design the extraction systems. So here, this is a mass balance, a differential mass balance. The last term there is actually the rate at which the solid, the component decomposes. The second term is the rate at which the solute is released into the solvent. And the first term represents the net rate of change of the solute content in the solid content, is the difference between the amount that has got transferred, that is the amount that the solute has lost, and the amount that the solute has lost by reaction. So now what we do here, in order to simplify the mathematics, now I'm a bit of an old-fashioned engineer, so I don't like to rush to the computer. Young students will first go to the computer. I probably go to the computer as a last resort. So what I did was, if you look at here, the modeling of extraction systems, you will see that the rate at which any bioextraction systems, you will see that the rate at which any bioactive comes out of a solid is usually an exponential function. So I've just assumed an exponential function where the concentration of the solute in the solid phase is actually an exponentially decaying function with some rate constants. So if I assume, I can simply reduce this differential equation to an algebraic equation, and that simplifies the process considerably. Similar to the solid phase, you can also write a mass balance on the liquid phase and say that the rate at which the solid concentration or the bioactive concentration in the liquid phase changes is equal to the rate at which it receives the mass from the solid phase and the rate at which the decomposition occurs in the liquid phase. So when you do that, now you can combine the two equations, solve them, and in fact, The differential equation can also be solved by a high school mathematics. So it simplifies considerably, and we have an expression for the concentration of the bioactive in the liquid phase, and that's given by this equation. I just reproduced that equation, but what is interesting is we can actually do some test that equation by taking it to some extremes. So if the solute transfer occurs very rapidly, that means the solid phase decomposition does not occur. So you will be able to then reduce that equation by simply putting K1 and K2. K1 is 0. In the second case, what we have done is to assume that the rate constants for decomposition in the solid as well as the liquid phase is the same, and there is a good reason for the two to be the same, because both are essentially aqueous in nature. So, and the decomposition is by heat. So if you assume that, again you get a simplified equation. Heat. So if you assume that, again you get a simplified equation. And just to validate it, if there was no decomposition, this equation also reduces to a simple equation which is very well known. So this actually tests the validity of the equation. This equation also tells us the concentration goes through a maximum. I'm sure all those who have done A-level mathematics, you know that there is something called turning point. So you have the concentration increasing, peaking, and dropping. So if you know that there is a peak, we can now mathematically identify the concentration. We can also identify the time it takes for that peak to be reached. So once you get that, that should be the operational condition. That's the reaction. That's the time for which you have got to run the reactor for. So now there is no point in just developing mathematical model experimentally. So what we did was to use the solid phase was dried beetroot and carrots, and then the extraction of beta-carotene was done at very high temperatures, 90, 115, 135. These are pretty high temperatures. Nobody else tries it because they think all the bioactive will be dead. It doesn't happen like that, because you are controlling the time. And that's the important point to note. Don't just say something is sensitive to heat, so don't heat. That's not the logic. If something is sensitive to heat, find out how sensitive it is, and then heat it accordingly. So we then used a separate batch for each extraction time, and then each time was also triplicated. So it's pretty extensive experimental procedure, and then of course we also analyzed the bioactive spectrophotometrically. Not only that, the spectrophotometric, most people do spectrophotometric analysis, but they don't test it with HPLC. We did both. That's important. So now you see what happens here. The concentration increases over a very short time and then gradually drops. So it reaches the peak, and that you can see the model as well as the experimental points around the model. So if you don't do the shorter time sampling, you will only get the decreasing. You will miss it, and that is why you've got to be very careful when you decide what the time should be. So what we then did was to compare the productivity of beta-carotene at different temperatures, and you will see that you get extremely high productivity at temperatures of 85, 90 degrees. Sorry. And here we have sort of, a comparison between what the values of productivity which earlier researchers have obtained and what we have got, and we've got significantly higher without using any ultra solvent, nothing. It's just that we are able to identify the right operating conditions. Now, what I will do is to talk about the thermal sensitivity. People talk about beta-carotene being sensitive to heat, but then we have to understand how thermally sensitive it is. Does it instantly degrade at every temperature? Does it take a while to degrade? So that's what we will talk about. So the degradation of beta-carotene followed first order kinetics. Beta-carotene is fairly stable up to temperatures of 180 degrees. That's a very high temperature, and it is stable. And then you also have different isomers of beta-carotene. You have the trans, the 9-cis, you have the 13-cis. So what we have done is to develop a network model to identify how the beta-carotene will decompose. So most of the beta-carotene that is present in carrots is actually the trans variety. So the trans beta-carotene can reversibly degrade to form 9-cis, or it can also form 13-cis. And then of course these cis isomers can also irreversibly thermally degrade. That is possible. The trans beta-carotene can also directly thermally degrade. So this is the entire network of possible operations. Yeah, this is the network. So this is what happens here. So what we did was to then and we found out the rate constants for the degradation. So these are the differential equations which were solved. I'm not going to go through that, and that's what we get. And from that we derive the various rate constants. So now comes the health benefit from a product formulation point of view. So you have beta-carotenes. Beta-carotenes is a source of vitamin A. It is soluble in oil. So what we say is, why can't we have oil enriched with beta-carotene being sold in the market? Now, just because a product contains beta-carotene, it doesn't mean our body will accept it. Let's accept that first. You have to do the trials. So what we did was to take beta-carotene fortified oil. It has a wonderful color. Beta-carotene has a very nice color, golden color. So then in that oil we fried potato chips. Okay, and absolutely golden potato chips, much better than any chips that you can get in the market. And then what we did was to feed it to 10 volunteers. And so these are the human trials. Incidentally, I'm an engineer, I know nothing about human trials, so I had to go to colleagues who were familiar with human trials. So what they did was to feed them 50 grams each, and then did a blood extraction over a day, and then looked at the beta-carotene level in the blood plasma. And you can now see that this graph represents how the beta-carotene level increased in the blood. So clearly by frying in oil that contains beta-carotene, you can reduce vitamin A deficiency. That's what we are trying to prove here. Is that clear? So I hope I have sort of taken you through the whole journey of extraction, mechanism, and then design of extractors, and then product development, as well as making sure that the product is health benefit. So that's the main message that I would like to convey. Thank you very much. And these are my colleagues, sorry. Rahul was the PhD student, Jose Maria Orunashi, and then Dimitris are my, contributed to this project. Thank you.
Thank you, Prof. Niranjan, for the fruitful